Let's talk about systems of linear equations in 3 variables. So since there are 3 variables, solutions are going to be ordered triples instead of ordered pairs, right? So ordered triples x, y, z. And these ordered triples have to satisfy all 3 equations. They have to make all 3 equations true, okay? Since we've gone up a dimension, the graphs of equations in 3 variables are planes, not lines. And it's a little bit difficult to visualize those, but anyway, they have kind of a similar interpretation, right? It's possible that the planes might never all intersect, so you could have no solution. It's possible that the planes intersect in a line, in which case you have infinitely many solutions, or maybe all 3 planes represent the same plane, so you have infinitely many solutions in 2 dimensions. And then it's also possible that the planes intersect at a single point, which is the most common scenario. But anyway, if during the course of solving a system, you end up at some point with a contradiction, then there's no solution. If you end up at some point with an identity, then there are infinitely many solutions, okay? The method that I'm going to use for solving systems with 3 equations with 3 unknowns is I'm going to use the elimination method on 2 of the equations to eliminate one of the variables. Then I'm going to use the elimination method again on a different set of 2 equations to eliminate the same variable that I eliminated in step 1. Once I've done that, then the system I'm left with will be a system of 2 equations with 2 unknowns. And then I can just solve that using the methods that we talked about in section 1.5. So let's look at some examples. So looking at this example, I want to be able to solve, or I want to be able to eliminate the same variable in 2 of the equations. So looking at this, I think eliminating the y's is a good candidate, because I can just add the top equation to the bottom equation as they are, and the y's will become eliminated. And then to do that again with a different set of 2 equations, I could use, for example, the top equation and the middle equation, and all I have to do is multiply the middle equation by 3 to get the y's to cancel. So I think that's probably the best strategy here. You could also potentially eliminate the z's or the x's. It's up to you, but what seems easiest to me is to eliminate the y's. So I'm going to do that by adding the first and third equations together. If I add the first and third equations together, so x plus 3y plus z equals 0, and 3x minus 3y plus 2z equals 2. If I add these things up, I get 4x, the y's cancel, plus 3z equals 2. And then the other thing I said I could do would be to add the first equation and 3 times the second equation. So I'm going to do that over here. I'm going to have, again, x plus 3y plus z equals 0. But then the second equation is going to become 6x, right? 6x minus 3y minus 15z equals, whatever 3 times 14 is, 12, carry the 1, 42. Okay, we have these things up. And we're going to get 7x, again the y's cancel, minus 14z equals 42. So now I've got these 2 equations. Notice that I've eliminated y from both of them. And so I've just got a system of 2 equations with 2 unknowns. So it should be fairly easy to solve just using the stuff that we did in, in 1.5. So looking at these 2 things, well, I'm thinking of eliminating the x's probably. I think the common denominator, so to speak, between 4 and 7 would be 28. So I'm thinking of multiplying this one by -7 and this one by +4, and then adding them together. So let's do that. So I'm going to do -7 here, positive 4 here. Actually, maybe to keep the work a little bit easier to keep track of, let me just rewrite this system now. So I've got 4x plus 3z equals 2, and I've got 7x minus 14z equals 42. This is my new system. And I'm going to take this now, I'm going to do negative 7 times the top and positive 4 times the bottom to get negative 28x minus 21z equals negative 14, and 28x minus 14 times 4, that should be 7 times 8, so that should be 56z equals, I keep doing, I keep having these big answers, so 168. That wasn't terrible, actually. Look at me complaining. It wasn't that bad. I add these up. I have negative 77z equals 154, I believe. Oh, and look at how nicely that works. 2 times 77 is 154, isn't it? So z is negative 2. Oh, this problem was rigged. Okay. So z is negative 2. Now we need to go back and find out what x and y are. And I can do that by back substituting. So I know that z is negative 2. I also have these two equations, so I can plug this into one of these two things to solve for x. I think the first one looks easier, so I'm going to say 4x plus 3z equals 2. So 4x equals 8, so x equals 2. Okay, so I've got z, I've got x. I can take those now and plug them into one of the original equations to solve for y. I'm thinking the top one's probably the easiest, so I'm going to say x plus 3y plus z equals 0. So I'm going to say x plus 3y plus z equals 0. Can it really be that easy, right? 3y is 0, y is 0. So my solution set then is going to be, and make sure to get these in the right order, it should be x, y, z. X, y, z. Okay, so that's that one. It's kind of a longer, more tedious process. Doing one of these is like doing 3 of the systems of 2 equations and 2 unknowns, right? So it does take quite a bit more work, but it's not more difficult. It's just more. It's more to keep track of, I guess. So I guess the difficulty you might have is keeping track of your work. So come up with a good system that you like for organizing your work. This system works out for me, I think. Let's look at another one. Oh, well, this one's kind of nice. The top one already has x eliminated. So all I need to do really is eliminate x from one of these, or from this other set of equations, which I can do quite easily by multiplying the bottom by negative 2. So if I multiply the bottom by negative 2, now I'm going to have 2x plus y plus z equals 9, and negative 2x minus 4y minus 4z equals negative 6. If I add these up, x's are gone, negative 3y minus 3z equals 3. So now I can put this one together with this original one that I had, and that's a system of 2 equations with 2 unknowns. So, so I should be able to solve that one pretty easily. Actually, this one is very easy, right? This is already set up for me to just add these up and see what I get. Right? I eliminate the y's that way. Get negative 4z equals 8. So z is, once again, negative 2. Is that odd or what? Yeah, but we're getting z equals negative 2 again. Okay. Now I can take this and plug it back into this one or this one. Probably this one's easier. So I'm going to say 3y minus z equals 5. Okay. And then I can take these two, plug them back into, one of these equations or something to solve for x. So I can say 2x plus y plus z equals 9. So x equals 5. And there you go. So my solution is 5, 1, negative 2. So that's that idea. I think I have like 3 more examples here. So let's just hammer them out. Let's go on to the next one. Remember, if I'm moving too fast, pause the video, rewind the video. A good thing to do also would be to pause the video and try each of these problems before I work them out, see if you can do them on your own. Okay, but I'm just going to hammer through these. Let's see. What do I want to eliminate here? I think any of them actually would be not terrible to eliminate. Here's what I'm going to do. I'm going to eliminate the x's. So I'm going to start off multiplying the top by 4. And then I'm going to use the middle equation just as is. That'll eliminate my x's. Okay, so far so good there. Okay, so now what else can I do? Well, I can multiply the bottom equation by 2 and then add that to the middle equation. So middle equation stays the same. Bottom equation is going to become 4x plus 10y minus 4z equals 2. Add those up. Okay. These two equations now form their own new system. 3y minus 4z equals negative 9, and 9y minus 12z equals negative 27. Oh, and you might notice something fishy already. If you don't, then all it takes is one more step for you to see it. So let's say that we want to eliminate the y's, right? The easiest way to do that would be to multiply the top one by negative 3, right? So we're going to have negative 9y plus 12z equals positive 27. The bottom equation stays the same. 9y minus 12z equals negative 27. I add these things up, and I get 0 equals 0. So what does that tell us? Right? Well, this is a true statement, right? It's an identity. So it tells us the same thing that it told us in the previous section, right? It tells us that there are infinitely many solutions to this system. So we still want to describe them though, right? So we want to describe the solutions x, y, z. To do that, I think we can solve, I think we'll just let z be itself. And then we'll solve for y in terms of z. And then once we have that, we can solve for x in terms of z. Okay? So let's do it. So we're going to let x be itself. Well, now let's solve for y in terms of z. I'm going to take this one and solve for y. I'm going to say 3y equals 4z minus 9. That means y equals 4/3 z minus 3. Okay, so I've got y. I'm just going to let z be itself, right? So I've got z, I've got y. Let's figure out what x is. I think it would be easiest in the top equation. So I'm going to say, x plus y plus z equals 5. That implies x plus y plus z, which is playing itself, equals 5. Now I can combine like terms and solve for x, right? So I can say 4/3 z plus 3/3 z would be 7/3 z. I can add the 3 over. And then if I want to solve for x, I should move the 7/3 z over. So I'm going to say x equals negative 7/3 z plus 8. And there's x. So putting it all together then, my solution set is going to look like this. It's going to be numbers of the form negative 7/3 z plus 8, right? That's x. 4/3 z minus 3. Okay, that's y. And then z is playing itself, right? Where z is allowed to be any real number. So there's that solution set. Again, this solution set generates all of the solutions to this system. This system has infinitely many solutions, but not all ordered triples are solutions. Only the ordered triples that have this format are solutions. So if you wanted to see some examples, you could plug in, say, 0 for z. If you plug in 0 for z, you get 8, negative 3, 0. That's a solution to the system. Another solution would be if you plugged in, say, 3 for z. If I plugged in 3 for z, then I would get negative 7 plus 8 is 1. 4 minus 3 is 1, 3. Right? So that's another solution to the system. And you could get a whole bunch of other kinds of solutions. Okay, but that's that one. Let's move on. I smell another kind of fishy one here. Looking at all these numbers, they're all like multiples of each other. So it just seems like, I don't know. For example, if I tried to get rid of the x's, I could have the top one and the bottom one as they are, right? But when I go to do that, I get an identity right off the bat. So that tells me once again, I've got infinitely many solutions. But see, on this one, I had infinitely many solutions, but I only had one variable, right? Like I could describe the other 2 variables in terms of the third one. But on this one, I'm not going to be able to describe, like I have infinitely many solutions, but I'm not going to be able to describe them in terms of just one variable. I'm going to have 2 variables. I'm going to have 2 degrees of freedom here. Because I got this identity right off the bat. So what I'm going to do is I'm going to let, it doesn't really matter which ones you let be themselves. right? You can choose any two you like, but I'm going to let x and y be themselves, right? So I want to describe the solution set x, y, z, and I'm going to let x and y just be themselves, right? And then I'm going to solve for z in terms of x and y by solving one of these equations for z. It doesn't matter which one. Maybe I'll take the top one. So 2x plus y minus 3z equals 7. Solving this for z, I would get negative 3z equals negative 2x minus y plus 7. All right, just moving these guys over to the other side. And then dividing through by negative 3, z equals 2/3 x plus 1/3 y minus 7/3. So my solution set is going to look like this. It's going to look like numbers of the form x, y, z. Where x and y are allowed to be any real number. Okay. Graphically, what's going on here is that in this problem, the three planes coincide in a single straight line, and this is the order triple that describes that line. This one, the three planes are all exactly the same plane. They all describe the same plane, and you can see that because they're all multiples of each other. So they all describe the same plane, and this is the ordered triple that describes that entire plane. That's why you have two degrees of freedom, right? Two dimensions here, right? So here you just had a one-dimensional answer, right? Because they coincided at a straight line. And here you have a two-dimensional answer because they're coinciding on an entire plane. So that's that idea. Let's look at one more. 2x plus 2y plus 2z equals 12, etc., etc. What do we want to eliminate? Looks like probably eliminating the y is going to be the easiest, so that's what I'm going to start out trying to do. I think I'm going to do that by I'm adding the first and second ones, but first I have to multiply the second one by a -2. So let's see. We get top equation stays the same. Bottom equation is going to become 6x minus 2y plus 22z equals positive 12. So I add these up. I get 8x, y's cancel, 24z equals 24. Okay. Then I can do the same trick, add the first one to the third one. I'm going to have to multiply the third one by -2 as well. I'm going to get 2x plus 2y plus 2z equals 12. And -4x minus 2y minus 8z equals 16. I add those up. I have -2x, the y's cancel. I have -6z, and that equals 28. Okay, so now I've got my new system. And so to solve this system, I think probably eliminating the x's, and I would do that by multiplying by 4 on the bottom equation. I'm going to get -8x, -24z, and 28 times 4, 32, so 112. Oh, is that right? I better check. 4 times 28. I'm getting tired. I've recorded like 6 of these lectures today. Okay, 112. Yep. We add these up. The x's cancel. The z's cancel. We get 0 equals some big, huge number, right? 138, which is not a true statement. That's a false statement. So what this tells us is that there's no solution. And we're done. We don't have to try to describe the solution set because there is no solution set, right? It's empty. So there you go. Right, so we like these ones. Once again, we like these ones. They're the easiest ones because once we get a contradiction, we're done. Okay, so that's that. We've seen several examples. I just wanted to mention quickly about applications, okay? There are tons of applications of systems of equations in the real world, right? Search engines use systems of equations, right? They're used in finance, they're used in biology, they're used to predict the weather, all kinds of stuff, man. Systems of equations are everywhere. So here's an interesting video. It's a TED Talk, and it's by a professor who teaches at Stanford, and she gives a lot of really great examples of applications of systems of equations. And she gives a lot of really cool visuals of these systems too. So I would strongly encourage you to take a look at this because it'll give you some sense for where systems of equations are actually used in the real world. As I said in the previous section, the application problems that we look at in algebra class tend to be pretty cheesy because it's hard to come up with a good example of where a system would be useful in the real world that only uses 3 variables, right? So that's why we end up doing these really kind of weird, cheesy examples in class. But if you want to get a better example for where systems are actually used in the real world, take a look at this video. It's really, really interesting. I'm just going to give you one cheesy example, though. Because this is one that we can do by hand, right? It's one that doesn't, like these examples are going to have like thousands and thousands of variables in them. This will just have 3. So, and the thing is, in order to be able to solve these kinds of systems, in order to know how to set them up, you have to have some understanding of how to solve and set up these kinds of systems. And so that's why we practice them, even though it's a little bit cheesy. Anyway, this says, suppose that you're on a diet which requires you to drink Soylent for breakfast every morning. I wonder if any of you know what Soylent is. Soylent is like this, it's this meal replacement drink. Anyway, I could go off about like Soylent Green and there's this funny movie. Oh, what is the name of that movie? I can't remember. Maybe the movie's called Soylent Green. I can't remember. Anyway, it doesn't matter. So you're on a diet, requires you to drink Soylent for breakfast every morning. Unfortunately, you open your cupboard and discovered that you're out of Soylent. However, you do have 3 boxes of cereal, Cheerios, Cinnamon Toast Crunch, and Rice Krispies. You also know that your daily serving of Soylent contains precisely 245 calories with 6 grams of protein and 7 grams of fat. The pertinent nutritional information per serving of the cereals is as follows. So 1 serving of Cheerios is going to have 120 calories with 4 grams of protein and 2 grams of fat, and so forth for Cinnamon Toast Crunch and Rice Krispies. Clearly, you would want a bowl of Cinnamon Toast Crunch because it's delicious. That's my own personal bias seeping into the math, right? But Cinnamon Toast Crunch is very tasty. However, you want to stick to your diet, right? So question is there some kind of combination of the servings of these cereals that you could eat to imitate the calorie, protein, and fat counts in the Soylent? Well, let's see. This is completely made up, by the way. Like, don't take my word for it. In fact, yeah, this is completely wrong. I know for a fact that this is not the nutritional information in these cereals, okay? Don't sue me either if you're like an heir to the Cheerios fortune, right? If you work for General Miller or whatever that cereal company is. Yeah, don't sue me. Anyway, let's see if we can figure this out. So what I want to do is I'm going to call the number of so let's make another column for the number of servings. This is the number of servings that I'm going to eat of each of these kinds of cereals. So for Cheerios, I want X servings, for Cinnamon Toast Crunch, Y servings, and for Rice Krispies, Z servings, right? And what I can do is I can figure out how many calories in total I'm going to eat, how much protein I'm going to eat, and how much fat I'm going to eat, right? So the number of calories I'm going to eat from the Cheerios is going to be 120 times the number of Cheerios servings that I eat, right? So for Cheerios, so for calories, maybe I'll say this. For total calories, it's going to be 120 times the number of Cheerios servings I eat, plus 130 times the number of Cinnamon Toast Crunch servings I eat, plus 105 times the number of Rice Krispie servings that I eat. And I want that to equal the number of calories in my Soylent, right? So I want that to equal 245. So that's one place that I can get an equation. Another place I can get an equation is to look at the total amount of protein that I consume. Total amount of protein is going to be 4 times the number of servings of Cheerios that I eat, plus 3 times the number of servings of Cinnamon Toast Crunch that I eat, plus 1 times the number of servings of Rice Krispies that I eat. And I want that to equal 6, right? Because I want 6 grams of protein. So I want that to equal 6. And then finally, I can get another equation if I look at the total fat that I consume. So that's the total fat I consume is going to be 2x plus 5y plus 2z. And I want that to equal 7, right? I want that to equal 7 grams of fat. And there's my system, right? There's my system of 3 equations with 3 unknowns. And I can solve this thing. I'm not going to do it. I'm not going to actually solve this system. My main concern was making sure that we could set it up, right? And we can set it up. Now, if you wanted to solve this, you would follow the same strategy that we've been, following to solve all of these other systems of equations, right? So I'm not going to bother actually going through and solving this, but it is interesting. You could come up with a combination of cereals to eat that would mimic your consumption of Soylent, which in my mind is like, why eat the Soylent then? Eat the cereal, it's better. Actually, Soylent's not that bad. I've had Soylent before. It kind of tastes like Cheerios, to be honest. It tastes like crushed up Cheerios or something. But anyway, but I'm guessing that probably Soylent has some other stuff, vitamins and minerals and stuff that you probably don't get from the breakfast cereal, which is why it's maybe advantageous to eat Soylent. But that's all I'm going to say here. We'll see you in the next section.